All right, let's get started. Number one. Okay, consider the curve given by x squared minus xy plus y squared equals 4. Find 2 points on the curve. So they're not even asking for derivative yet. We're just asking about ordered pairs. Anything with ordered pair is just the original equation. There's no need for anything with the derivative. Okay, now they give us some information here. So x equals 0. We can go ahead and replace 0 in for x. And ordered pairs includes y values. So we'll see what happens when we insert 0 in for x. All right, so the first 2 terms will drop out. All I'm left with is y squared equals 4. Take the square root. Now, when you take the square root of both sides of an equation, a plus or minus will pop up. And plus or minus root 4 is just plus or minus 2. So that means when x equals 0, we have 2 different y values that pop up. So here we have our 2 points. Okay, any questions here? Okay, part B, find the derivative implicitly. So implicit, even though they didn't, the problem did not have to say implicitly. It could have just said find the derivative, find dy dx, and we can look at this and determine on our own that this does require implicit because we see multiple y variables. We expect 2 dy dx's to pop up. And then this xy is indicating to us that there's also a product rule involved. And we got to watch out for that negative sign. So I'm putting in parentheses as a reminder that when I go through the product rule, I still want to keep that parentheses so I don't forget about the need for that negative to distribute through the results of my product rule. So x squared becomes 2x minus, I'm going to give myself some room here. Spell out exactly what I need. Build out my derivative. Okay, so we just give the derivative product rule whatever it needs. F prime is asking for x's derivative, so x becomes 1. G is just the original G term, no changes. Back to F, x is just x. And then G prime, y's derivative is 1 dy dx. Okay. So we're done with product rule. Now we have 2 more terms left, 2 more terms to find our derivative. Y squared becomes 2y, but we are asking for y's derivative, so dy dx will pop up. And then 4, don't forget the 4 is also being impacted. 4 doesn't stay a 4, 4 goes to a 0. Okay, question so far? Yeah. First y did not get dy dx because it's only asking for g, right? You only do dy dx if the product rule is asking for the derivative and there's y involved. Because this is a singular term. So if it's a singular term, I'm just jumping from this term to find the derivative. I'm just doing power rule. Okay. Right. So sometimes within product rule, there are times when some things are not requiring the derivative. If it's just asking for G and F, then you're just going to take whatever G and F gives you. If it's a singular term, yeah. I mean, within product rule, you just have to know that not every term is going to get a derivative treatment. But yeah, if it's like 2y or 4y squared, or if it's just power rule for that one term, then dy dx will be involved. Yes. Mm-hmm. Okay. So let's do okay, so let me say it this way, that we only are going to get a dy dx to show up if within product rule something is asking for the derivative. So if you see how G is not asking for the derivative, G is just asking for us to take whatever G shows us. So if within product rule, if something is not asking for the derivative, there's no need for us to find the derivative. If there's no need to find the derivative, there's no dy dx that shows up. Okay. So yeah, so we just have to do whatever product rule tells us. And also, you look at how many dy dx's that show up, and that's, however many y's you have, that's how many dy dx's show up. So if we have a dy dx here, that's too many. So hopefully, if you count the number of y's, that will help remind you, okay, look at your second line, and there should be the same number of dy dx's as the number of y's. That's right. I'm not deriving G and F because G and F is not asking for the derivative. It's just asking for me to pull down whatever G and F is showing me. You only make changes to G and F if F prime and G prime is asking you to do it. Yeah. Okay, good. Any other questions there? Yeah, so it's an important step. I mean, this is the most important step in the problem because this is the only calculus in the problem. The rest is just cleaning up. Okay, so now we're asking to find the derivative, dy dx. We have our dy dx variables show up. So now we just have to rearrange and try to find a way to get dy dx to be by itself. I'm going to distribute the negative through. All right, so I have 4 terms here, but I want to collect the dy dx terms on the same side. So I'll leave these 2 on the same side. I'm going to go ahead and move these 2 terms on the other side of the equation. Okay, factor the dy dx out. Divide the parentheses over. So I know dy dx looks a little strange from other derivatives, but it is still a derivative equation. So if I give it a full order pair, in return, it'll give me a number, and that number will correspond to how steep that point is on this curve, whatever this curve looks like. Okay, so it's all of this is just a slope formula. So part C, use the derivative to find the slope of the lines tangent to the curves at the point found in part A. So it's basically saying, okay, so I have these 2 points that live on the curve. What are the slopes at these points on the curve? So I have my slope formula. I'll just take each point, insert into the derivative, and that way I can know not only where the point is on the graph, but also how steep that point is on that curve. So I'll start with 0.02. So if I want to plug something into the derivative, this is the notation that's typically used. In the past, we would say like just f prime of 0, right? But this derivative requires more than just the x. It requires the x and the y. So we use this notation to say, okay, I need both the x and y inserted into the derivative in order for me to get that number that I'm looking for. Right, so all I'm doing is replacing every x and y with 0 and 2, seeing what numbers I get back in return. I get 2/4, which is 1/2. So at this point, there's a slope of 1/2. There's a second point, 0, -2. I'm going to insert that order pair into the derivative as well. Okay, -2 over -4 is 1/2. So for part D, write the equations of the line tangent to the curve at the points above. So I'm going to find the equation of the tangent line here, and then find the equation of a different tangent line here. Both I'm going to go through y minus y1 equals m times x minus x1. So point slope form. Yeah. Mm-hmm.
Put it to level 5, right?
Not if it's an inside function. So you're asking for chain rule and what?
Okay.
Chain rule and Pearson. Yeah, so I can do an example real quick here. Let's say I had x is equal to x plus y squared cubed. Okay, if I want to find the derivative, x becomes 1. This one has an outside and inside feature. Outside will be parentheses cubed, inside will be the x plus y squared. So I know I got to go through chain rule. So outside's derivative would be 3x plus y squared squared, right? Parentheses cubed becomes 3 parentheses squared. We don't touch the inside. But now that we're outside of that expression, now we can work on the inside portion. So now we can just ask, okay, what is the derivative of each of these terms? Because both of these are power rule. So x becomes 1 and y becomes 2y dy dx. Yeah. And also you look at your equation here, there's only one y. There's only one y instance in this equation, so you're only expecting one dy dx to pop up. Okay. All right, part E, set up and write the equations, but don't solve in order to find the vertical and horizontal tangent. So we know horizontal tangent is where you set the numerator of your derivative equal to 0. And then your vertical tangent is where you set the denominator of your derivative equal to 0. Okay. It says don't solve, so just set up the equation. Any questions on the first page? Okay, number 2. Okay, it says if G is differentiable everywhere, and G of X is equal to this function here, find A and B. So A and B are constants. And so we'll treat them like constants. So we know that we have 2 different graphs, and the 2 graphs are, we want them to meet at -2 in a certain way. We want them to meet in a way where they're going to have to, they want them to connect, share the same y value, but we also want them to connect in a way where it's going to smooth transition. So the slope at -2 for one curve is going to match the slope of the graph on the other curve. So here's the continuous feature of what we want. So we want the 2 graphs to share the same y value at x equals -2. So all I'm doing is I'm just setting the equations equal to each other, because this represents the y value of one graph. This represents the y value of the other graph, and I just want them to be in agreement at -2. Now, I only care that they are sharing the same y value at -2, at x equals -2. So I'm just going to go ahead and replace every x with -2, because that's the only point that we're really concerned about. So I have -48 minus 32 plus 8. So once I'm here, I'm a little stuck because I can't really solve for A and B without having help from another equation, right? I have two missing variables here. So I have to rely on another part of my property here, which is the differentiable portion. That means we want them to share the same slope. So differentiable at x equals -2. Now, in order for us to do anything with slope, we have to get to the derivative, right? So the derivative will tell us information about the slope. And we'll treat A and B like constants. Now, we're going to find the derivative, but each term, we just go through power rule. Now, the first term does not have any A's or B's inserted in them, so we can just find the derivative as is. So 6x cubed becomes 18x squared minus 16x. 8 goes to 0. Okay. Ax plus b, what's ax's derivative? Just a, and the b goes to a 0, right? If it was 3x plus 4, you would just make it 3 plus 0. So same thing, ax plus b would just be a plus 0, which is a. Okay. We know that we only care about these 2 curves sharing the same slope at x equals -2. So replace every x with -2. Okay, so 18 times 4 plus 32. Okay, so once you have your A value, 104, insert back into your first equation because you need some resolution, right? I have A, but I still need to solve for B. So plug 104 in for A and then just solve for B. All right, any questions with how to proceed with these types of problems? No. Okay. All right, now we have our graph. We're asking for h prime of 2. We look at how this problem is set up. This is a requirement. We need to go through a product rule here because f of x and g of x are multiplied by each other. And we see two x's, right? So there's two distinct expressions that are outside of one another. We got to go through product rule. So let's go ahead and build our product rule. So h prime of x is f prime times g plus f g prime. Okay, replace every x with 2. Okay, so now we go to our graph. We're either pulling the y value or we're pulling the slope from this graph. Okay, so f prime of 2 is asking for the slope of the f graph at 2, and the slope of this f graph, it's a negative slope. And pick 2 points here. I go down 1 over 1. My slope is negative 1. G of 2 is asking for the y value of the g graph at 2, and the y value of g graph at 2 is 2. Back to f of 2. F of 2 is this graph here. The graph of f of 2, y value is also 2. And then finally, g prime of 2. G prime of 2 is asking for the slope of this dotted line here. And this dotted line, it does change to slope 0, but it's still part of this diagonal line to at 2. And the slope of this line is a positive 1, right? Up 1 over 1. Okay, and then we just add those numbers together. Negative 2 plus 2, 0. Okay, part B, w of x equals f of g of x. What rule do we use here? Chain rule. This is inside, outside, inside, right? So we have to go through that process. Just make sure that you can recognize the distinction between product rule and chain rule. Right? Product rule has 2 x's. Chain rule still has f and g, or still has 2 different functions, but only has 1 x. So that indicates to you there's a function within a function. They're not outside of each other. Okay, so we'll do outsized derivative first. Times insized derivative. Okay. So now replace every x with 3. Now, this is too much to do in just one step, so let's break it down into more manageable steps. Let's see what feels easier to do. Let's just figure out what we can find. We see in front of us. We can find g of 3, we can find g prime of 3. Let's go ahead and find those values, replace them with numbers, and then we have a little bit more clarity as to what else we need to do. Okay, so g of 3 is asking for the y value of the g graph at 3. What's the y value of the g graph at 3? Well, it's asking, well, what's the y value though? The y value. What's that y value? I know it's a decimal value, but we can kind of estimate, right? 2.5. 2.5, right? It's between 2 and 3, so 2.5. So I'm replacing g of 3 with 2.5, but sorry, yeah, with 2.5, but I'm not changing anything else out in here, right? I'm still keeping that f prime, I'm still keeping that parentheses. I'm just replacing that g of 3 there. Okay. What's g prime of 3? 0, right? That's a slope of 0. Now, we know anything times 0 is going to be 0, but just for practice purposes, what is f prime of 2.5? So here's my f graph. F graph of 2.5 is here. It's talking about this point. What's the slope of the graph at this point? Yeah, it's still, I mean, it's a decimal value, but it's still sitting on this line. If I can find the slope of this line, then I know the slope at any point on that line, right? So it's part of this line here. This line is slope of -1, so. Okay, so chain rule tends to give students the most trouble with these types of problems, just knowing that it takes a couple of steps and we need that intermediate step before we can fully figure out that final step. Okay, part C, z of x equals 2 times f of x cubed. This is also chain rule. We clearly see an outside-inside portion, so let's build that out. We have our outside being that 2 bracket cubed. And then the inside is the f of x. All right, so we take turns with each portion. What's the outside's derivative? Hmm? 6 bracket squared. Yep, we're just going through power rule, right? All right, what do I insert in here? Just f of x, right? We're not ready for f prime. Some students want to put everything in one compact expression. It feels more efficient, but it's not the correct way to do it, right? We're not ready for the inside's derivative just yet. Now we're ready for inside's derivative. So f of x becomes, it's going to have its own space. Okay. Outside derivative and inside derivative will be completely separate from each other. Don't insert this in here. All right, so that's the hard part, building that derivative. Now replace every x with 0. Okay, so f of 0, we go to our graph. What's f of 0 equal to? 4, right? Okay, what's f prime of 0? Slope is -1, right? Okay, f of x. What rule do we use here? Chain rule as well. Right? It just seems strange that you were in the same function. We're inserting the same function into itself. So f of x, we got to go through chain rule as well. Okay, so outside times inside's derivative. Take the outside's derivative, leave the inside alone, or keep that inside as is, and then multiply by the inside's derivative times f prime. Okay, replace every x with 4. Okay, just understand chain rule requires multiple steps. We're not able to get to the answer right away. We kind of have to figure one thing out at a time here. So take care of that inside portion first, f4. We go to our f graph. F of 4 is equal to 2. But we haven't resolved that outside f prime yet. We just figured out what that inside part is. Times f prime of 4. So f prime of 4. The slope of the f graph at 4 here, this line segment has a slope of 1, up 1 over 1. Okay, so now for the last piece that we need to find is f prime of 2. F prime of 2 is asking for the f graph, the slope of the f graph at 2. The slope of this line segment here is -1, right? Down 1 over 1. Now that we have resolved all the function notation into numeric value, we can multiply the result. Okay, part E, if P of X equals G over F, find P prime, what do we have to go through here? Quotient rule. Quotient rule. This is what some students want to do. They want to say, okay, that's easy. I'll just do G prime over F prime, plug one in, find the slope, and that's it, right? So we can't do that. Right? We have to go through quotient rule. So it's backwards, right? Normally we're used to the top being the G, the F, and the bottom being the G. So good. Everybody good with quotient rule there? Okay. Replace every X with 1. Okay. Our focus is at 1 for both our graphs here. Okay, so G prime of 1, that's the dotted graph here. G prime of 1, asking for the slope of the G graph at 1. It's a slope of positive 1. F of 1 is asking for the y value of the f graph at 1. The y value is 3. Back to G of 1. G of 1, the y value there is 1. F prime of 1, the slope of the f graph at 1, negative slope, down 1 over 1, negative 1. F of 1 squared, so here's my f of 1. F of 1 is 3. Square that, 3 squared is 9. All right, any questions so far? All right, number 4. Find the derivative for our function here. What do you see? What's required here to find the derivative? Yeah, quotient. Let's build that outside inside portion, right? Let's identify them. Okay, so let's work on one piece at a time. 2 parentheses to the 7th. We have to go through power rule there. (14) parentheses to the 6th. Imagine this is 2x to the 7th. You do power rule, bring the 7 down, subtract 1 from the exponent. And what goes in here? Yeah, the original inside, right? We don't want to do anything with this, not yet, right? Not yet. Okay, so now that we're out of this first outer portion, now we're ready to take care of the second portion. And this inside portion, we can go through its derivative rule. And because numerator denominator tells us quotient rule. Okay, so f prime is asking for the numerator's derivative. I get 15x squared, and the 2 goes to 0. My g is 3 minus x squared, no changes. Back to f. Original numerator, no changes. G prime, denominator's derivative, 3 goes to 0. Negative x squared becomes negative 2x. All over my denominator squared. Okay, so you've earned the majority of the points if you get to this point, but I am going to ask you to clean it up into one fraction. So really, the only work that's ahead of us now is just to try to clean this up. Everything else is pretty much set. So I'll distribute that through, try to clean that up there. minus 4x. So this is my resulting cleaned up version of that. So now I just want to put it all under one fraction and just put all the parentheses that I can next to each other. So I'm going to highlight all the numerator portions, and that's what I want to place up top. Right, the 14, the parentheses to the 6th, that. So all that is in the numerator. So the denominator, I see a bunch of 3 minus x squared, but how many do I have in total? How many do you see? 8. 8, good. The temptation is looking at this and saying, hey, this looks like it's only 1 down here, and 1 plus 2 is 3. But don't forget that 6 also sees this denominator. There's a whole parentheses there. So there's 6 of these here. There's 2 of them here. 6 plus 2, 8. Yeah. Just 1 point. Yeah, because this is technically the answer. You have the answer here. This is the most important step here. This is just cleanup. Okay, so. Oh, yeah. So. Okay. So I spent more time on this. Let me just see what I can do with the second half here. Okay, particle motion. Okay, particle moves along a straight line. We have our position function here. Meters per minute is your units that we're going to be using. Okay, so go ahead and we go through power rule here. Now, if you are looking at this, thinking about how to find the derivative here, you can always pull that 4 out as 1/4 if it makes it easier. So if we bring that 4 down, 4 times 1/4 is 1. Subtract 1 from the exponent. That's why it becomes t cubed minus 3t squared minus 4t plus 0. There's my yes.
You also do like bring the 4 in front of the T on the top and then be like 4. So
That's fine. Yeah, you can do that. Acceleration is just another derivative down. So t cubed becomes 3t squared minus 6t minus 4. Okay, find when the particle changes direction. So this is simply relying on the velocity function. We talked about this. always set your velocity equal to 0, and then find your critical points. So set velocity equal to 0. I factor the t out. And I continue factoring, multiplies to be -4, adds it to be -3. I have -4 and +1. T minus 4, t plus 1. Now, if you look, I have 3 t variables, so I'm expecting 3 t values. It says all, see over here, all real numbers. So all real numbers tells us that we're going to include negatives as part of our domain. So negatives is also included. So on your number line, you're going to place -1, 0, and 4. Next up, we want to populate the signs in each interval. So I'm choosing numbers in each subinterval to test against my velocity function, or to plug it into the velocity function. So I have 4 regions, so I need to figure out the direction in each region. So -2 in for t, I get negative times a negative. That's, oh, sorry, a negative times a negative times a negative. So 3 negatives still remains negative there. -1/2, so that's negative, negative, positive. 2 negatives and a positive makes positive. Plug 1 in, positive, negative, positive. There's only 1 negative here, so negative. Plug 5 in, positive, positive, positive. Now, once you find your signs here, you can cross these numbers out. These numbers are not going to play a role when you write your intervals, right? You're just using the negative infinity, the -1, the 0, and the 4 positive infinity. Okay, so there's a direct direction change at all these t values because you see a change in sign, right? So at -1, 0, and 4, because velocity changes signs, right? So make sure you specify, don't just say because there's a change of signs. Specify what you're referring to. Sorry for the typo here. I meant for this to be particle moving left and then particle moving right. So moving left, you're just reading your velocity sign line. Negatives would be left and positives would be right. So -infinity to -1, the first and the third region is where we can expect this object moving left because velocity is less than 0. Particle moves right in the second and fourth region because velocity is greater than 0. Right, we've done particle motion every day for the past few days, so hopefully it's becoming more familiar and more comfortable. Okay, next up, finding average velocity. Know that the formula for average velocity is change in position over change in time. We do not touch the velocity function. So just x(3) minus x(1) divided by 3 minus 1. We find the positions at these values and then just enter in our calculator. And then your units of measure is meters per minute. Average acceleration, we don't touch acceleration. We use the function above it, is the change in velocity over the change in time. So v of 3 minus v of 1 over 3 minus 1. We just insert those values into our velocity function. And even though we don't touch acceleration, we're still doing something that is acceleration related because it's velocity divided by time. That is going to be meters per minute squared. Okay, find the particle's displacement. So displacement is just final position minus initial position, and that's it. We don't divide by change in time. It's just the change in position. X of 6 minus x of 1. Whatever it gets back in return, if it's positive, then keep it. If it's negative, keep it. There's no need to change your signs. Your displacement can be negative. Okay, Part H, find the particle's distance between 1 and 6. Now, distance sometimes requires more work if there is ever a change in direction, and there is quite a few direction changes over the course of this object's movement because we see all these change in signs, right? But we only have to consider the change in signs between our interval. So we're going from 1 to 6. If we're going from 1 to 6, there's only a change in sign at 4, so there's no need to worry about -1 and 0. So we just have to worry about the position at our endpoints and our position at 4. Don't do anything velocity related. Don't do v of 4, right? We're just looking at the velocity sound line to see if there's a direction change, and so that we can decide, do we need to use that location as part of our calculation. So we need 1 and 6 because those are our endpoints. We need 4 because there is a direction change from our velocity sign line. And then we just find the locations at each of those points. So we're not going to add these numbers together. We're going to pretend like we're walking between these locations, and then we're just counting our steps. So between -1.75 and -31, if we subtract that, that will tell us how far we've walked. So we get 29.25 from -1.75 to -31. And then from -31 to 37, we do 37 minus -31. That's quite a bit of distance there. That's going to be 68 steps. So you walk to the left, 29 steps. You walk to the right, 68 steps. You add those together. That's your total distance. And the reason that I like to use that steps analogy is because that reminds you, okay, I'm taking steps here. So everything that I'm counting is positive numbers. So positive 29, positive 68. Okay, finally, is the speed increasing or decreasing? We have to look at velocity and acceleration. Velocity at 2 is negative, acceleration at 2 is negative. 2 negatives tells us that if we have the same signs, the speed is increasing. But don't just say speed is increasing because same signs. Specify what you're talking about. Say that's because it's the velocity and acceleration that have the same signs. Okay, at t equals 5, is the velocity increasing or decreasing? This is not talking about velocity. This is talking about the rate of change of velocity. So this is just describing acceleration. So we just look at acceleration. Acceleration at 5 is 41. That's a positive number. So velocity is increasing at t equals 5 because acceleration is positive. Okay. And with good reason, this throws a lot of students off because you see the word velocity and you just naturally want to put 5 into velocity, but the word increase and decrease kind of changes what it's talking about. It's talking about the rate of change of it, not the velocity itself. Okay, I'll come around and see if you guys have any questions. What's the slope? Yeah, that will be undefined. This be also.
So it would just like make the whole thing.
That's right. Walking is all awesome.
Which is acceleration.
Right. Anything accelerated is going to where
So you feel that it's why don't you write
yeah, carry to the force of 4 minus 3 cubed minus 2 times 3 squared plus the should calculate it, just plug it all into that. They don't have to device.
Okay, so the derivative.
That's right. Right, this B is not a variable, B is a constant. So you repeat B like you would if it was y. So what's the derivative of y? Yeah, what's the derivative of B? A and B are constants.
Okay.
Treat them like constants. Yeah.
It's for a number.
It's 0.
That's right. Okay, something.
I know.
I think that's.
Like another. Like, I want to like being done, if you want a difference. Like it's on the quiz.
Yeah.
Oh, you put the front sheet, the page with the exponent and then. Okay.
Oh, worksheets. So worksheet 3.
Thank you.
Not there on that person.
That's right, yeah.
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 Give the velocity,
You go to, I'm with them.
give the,
Good eye.
yeah, so basically give some that's.
There's some problem.
Where should I sit?
There to be like a negative value. Bro.
Yeah. Well, because I said x equals 0, so all devices are disappear.
What is show? If you said x equals like 2, then we told y.
They have to go to the factory.
You like.
Yeah. I showed you what you showed. I didn't say that at all. I said, let's redo that around.
Am I allowed to take the test this period? Because I don't have a first period.
Sure, yeah. Uh-huh. You can sit in the back. Yeah, all my back seats are empty, so you can sit in the back. Yeah.
Okay.
Mhm.
Oh, it's not fair.